Okay, so let's look few of the questions from support vector machine. So the first question is, suppose you are using linear SVM classifier with two class classification problem. Consider the following data in which the point circled red represents the support vectors. So all these are the support vectors, right? So will the decision boundary change if the red points are removed? So let's suppose that you run the algorithm, and after running you got your optimal hyperplane or line, and now question is asking that if you remove this support vector that is the near to, you can say, the separating hyperplane, if you remove the support vector, then this hyperplane or this line will will have any change, or will it get change? So so uh, while running the algorithm, so the how how this works, that to make this optimal decision that this will be the separating hyperplane, so it uses these vectors, right? These support vectors, that is, that are the uh, near to this hyperplane, right? So if you alter this supporting vector, then that will have the effect on this hyperplane, so it will get changed. So the correct answer for this is yes. Right, now let's move to next question. Consider the data points in the figure. So we have given this data point, and if you see that we have different hyperplanes, right? Let us assume the black colored circle represents positive class, whereas the white circle represents negative class. Which of the following among h1, h2, h3 is the maximum margin hyperplane? So first of all, you have to know about what is maximum margin hyperplane, right? So 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 out of this h1, h2, h3, I have to see that which one is the maximum margin hyperplane. So uh, the the margin between the two classes should be maximum. So a plane should have the margin that should be maximum in separating these two classes, right? So overall point is that this street should be maximum width, right? So this street should have the maximum width in both side, right? If you if you if you so this is s3, right? If you look at this h1, h2, so this h2, right? So let me so this is h2, right? And how this is going to separate, uh, maybe like this. So but if you see, there's these margins, and if you uh, consider this h3, then this is how your street is going to look, right? So this margin and this margin. So the ultimate goal in SVM, or to make this maximum margin hyperplane, to maximize this, right? Given under the constraint that that we should have the that these all should fall uh, before this, and all these classes should fall under this, right? Under this constraint we have to maximize this margin, right? So if you consider this h2 and h3 hyperplane, then this margin is greater than this margin, right? So that was the main idea. So you do not have to waste this much of time to make a decision that what is the correct answer. You can directly look at and you can say that the s3 is the correct answer. I'm just giving you idea that how it works, right? Now let's look at this question number 3. The soft margin SVM is more preferred than hard margin SVM when, right? So so if you know the difference between soft SVM and the hard SVM, then you will easily answer this question, right? in in soft margin SVM we allow misclassifications, right? But in hard margin SVM we are not allowing the misclassification. What do I mean to say? That let's look at this example. So there might be chances that we may have the one outliner, right? So that may be here. So let's suppose that may be here. So this example, right? So if we are allowing the soft model, if we are allowing the misclassification, right? So that what we call the soft margin, right? So and for this you see that this has been misclassified, although this is your hyperplane, right? So what the question that the is more preferred than hard margin SVM. So when you will prefer this as a soft margin SVM when data is noisy and contains overlapping points. So in this case you can consider this soft margin SVM, because in hard margin SVM we cannot allow any kind of misclassification, right? So this if you take this example with the S3 hyperplane, then this is the hard margin classifier, hard margin SVM, right? Let's look at this question number 4. After trainee and SVM we can discard all example which are not support vectors. So if you look at this example, that example number 1, uh, if this is your separating hyperplane, then these are the support vectors and all these are the non-support vectors, right? So after trainee and SVM we discard all example when which are not support vector and can still classify new examples. So this statement is correct, right? Because because uh, because to make the prediction uh, we need only the support vectors, right? At the time of prediction, if we know that what are the support vectors, then we can easily classify. We do not, I mean to say, we do not have to have the that non-support vectors, right? And how, that might be the question, that how I am saying that. So so for that you will have to look at the derivation part, right? That how this algorithm works and why this only support vectors is required to make the classification, why not the non-support vectors, right? So So the correct answer for this is true, right? And this the same question was on the sample paper, right? So where there I have also given the answer, right? Look at this question. If gz is the sigmoid function, then its derivative with respect to z may be written in terms of so what is sigmoid function? That gz is equals to 1 upon 1 plus e to the power minus z. This is the sigmoid function. Now you have to take the derivative of this, and where we use this sigmoid function in logistic regression, right? Logistic regression, and you should know that what is the derivative of this. So d is the derivative, and also I have I think in the lecture or even in one of my question series that I have derived. I don't remember, but that this derivative of this sigmoid function is this. Right, now let's move to next question. The question number 8, in the linearly non-separable case, right? So if any data set that is linearly non-separable, what effect does C parameter have on the SVM mode? So okay, so this parameter, so by tuning this parameter you can have some kind of trade-off between your bias and variance, and you by allowing the trade-off between, or by tuning this parameter C, we we have the control between the trade-off of bias and variance. The overall point is that by tuning this, we may allow a low bias, or we may allow a high variance. What do I mean to say? That overall point is that we may allow, by varying this parameter C, we may allow misclassification also, right? So the correct answer for this is it allows us to trade off the number of misclassified point in the training point and the size of the margin. So the correct answer for this is C. Support Suppose that we have this this is the kernel function, that the radial kernel with appropriate parameter to perform classification on particular two class dataset where the data is not linearly separable. In this scenario, the decision boundary, so we are using this kernel function, right? So if in SVM, so you see that SVM, the total SVM is the you can say that it has two part. So the first part is the maximum margin classifier plus this kernel. So if you do not, if you are not making use of this kernel, this kernel function or this kernel trick, you can say that then this SVM is nothing but, you can say, the simple linear classifier, right? And if you are allowing this kernel function into your algorithm, right, when you are uh, training your examples for the maximum margin classifier with the kernel function, then in this case, if you have some data that is maybe uh, uh, not separable, not linearly separable, right? So in that case, using the kernel, can uh, you can transform. So using this kernel, the overall point is that you can transform this all these data points to higher dimension, and you can have the linear classification with the hyperplane, right? And and if you have already gone through the theories, then you have heard about this kernel trick. So what happens that in actual, we do not have to like uh, map from low dimension to high dimension. So we do not have to do this mapping, right? Right. So using this kernel trick, what you can do is, you without mapping, you can have this kind of non-linear classification, right? So what it is, suppose that we have RVF kernel with appropriate parameter to perform classification on particular two class dataset where dataset is not linearly separable, right? And we are using this kernel function, right? And so in this scenario, the decision boundary is the transformed feature space in nonlinear. The decision boundary is the transform feature. The decision boundary is in the transformed feature space is linear. So decision boundary in the transform space is going to be linear, so this is correct. The decision boundary in the transform, so in the higher dimension the decision boundary will be linear, this is correct. The decision boundary in original feature space is linear, no. If it is non-linear separable, then how it could be a linear, right? In the original feature space, this cannot be true. The decision boundary in the original feature space is nonlinear, so this is correct. So two options are correct, that is B and D. Okay, now let's look at this last question. Which of the following statements are true about the kernel in SVM? So kernel function map low dimension data to high dimension space, this is correct. It is a similarity function, yes, this is the correct. So overall point is that, if you have gone through the derivation of this maximum margin classifier, then if you see that there that at the end, everything is going to be depend on this dot product, right? So this dot product is nothing but calculating the similarity between the two vector, right? How similar they are. And we are extending this idea, and instead of using this, what we do, we use this some valid kernel functions, and we make use of kernel trick, and we do the separation in higher dimension space, right? So this kernel is some kind of similarity function, this is correct, and this statement one is correct. So both statements are true, correct, and that is C. Okay, that is all. We will look more questions similar to that, and I think we have already uh, I think 5 more videos that I have already covered, that you can refer. There I have solved a good question that you can refer. Okay, thank you.